To understand why this matters, look at this reality from the field. This is an industrial sorbent blanket, pictured here fully saturated and loaded with crude oil. For decades, this has been our shield against ecological disasters. But it hides a deep problem. Every year, millions of gallons of oil are spilled into marine ecosystems, posing a significant threat to global biodiversity and coastal economies. But here is the paradox: traditional synthetic sorbents, like polypropylene, contribute heavily to secondary microplastic pollution. We drastically need a biodegradable, highly efficient, and cost-effective alternative. What if the perfect material is something we discard every single day?
Approximately 10 hours later.
The answer might be sitting right on a barber's floor. Or, frankly, right on top of your head. This brings us to industrial deployment. First, we have sorbent booms. These are cylindrical tubes packed tightly with loose keratin fibers, specifically deployed on the open ocean, to contain and absorb floating oil slicks. Sorbent mats. These are flat, felted sheets, designed for shoreline protection, and cleaning up oily beaches and tidal zones. But why exactly is hair so incredibly feasible for this heavy industrial task? The answer starts with its hierarchical porous structure. When randomly interlaced, hair fibers naturally form a complex 3D porous matrix, providing a vast surface area relative to its volume. Because oil droplets possess exceptionally low surface tension, they rapidly diffuse between these hydrophobic fibers, a process that is highly thermodynamically favored. This capillary network creates an interfacial vacuum effect, acting as a continuous draw that pulls oil away from the water surface and locks it deep into the center. If we look even deeper, to the molecular level, we see the unique alpha helix structure of keratin. This right-handed helical conformation is tightly stabilized by dense hydrogen bonds, allowing for highly efficient packing of polypeptide chains. Furthermore, the coiled coil assembly provides the immense tensile and mechanical strength required to survive harsh marine deployment and turbulent ocean currents. Chemically, the mechanism is driven entirely by hydrophobicity. Keratin is packed with hydrophobic side chains that lower surface energy compared to water, allowing oil to wet the fiber surface instantaneously. Through van der Waals interactions and hydrophobic clustering, the system triggers a spontaneous attraction between oil chains and protein side chains, driving the Gibbs free energy below zero. This creates a highly selective binding mechanism that preferentially captures hydrocarbons, while completely repelling polar water molecules. The raw data confirms this superiority. Let's look at the metrics. Human hair keratin has a high oil capacity of 5 to 9 grams per gram, with 100% biodegradability. Unlike polypropylene, which leaves zero biodegradability microplastics, or raw cotton, which pulls in too much water, hair has very low water pickup, an absorption speed of less than 1 minute per liter, and can be reused up to 100 times. The science is clear. In conclusion, advanced keratin technology transforms a zero-value waste stream into a powerful shield for our oceans. Thank you for your time, and I look forward to taking your questions.